When a person is irradiated, the amount of radiation they have received is measured by the so-called dose. The dose is qualified usually by the words absorbed, equivalent, or effective to describe whether energy deposited or associated local or whole body biological damage is being conveyed. The most basic dose is the absorbed dose. This is the amount of energy that ionizing radiation deposits per unit mass of an irradiated material. The units are the Gray, and a dose of 1 Gray represents the absorption of 1 joule of energy in the form of radiation by 1 kilogram of the material being irradiated. The definition of the Gray in terms of mass means that the volume of the material irradiated to receive 1 unit dose depends on the density of that material. To illustrate this, consider 3 materials, air, water and glass, each receiving an energy of 1 joule over a material mass of 1 kilogram, i.e. a dose of 1 Gray. Air is the least dense, so a cube of air 94 centimeters across the sides would be required. For water to receive the same dose, a cube 10 centimeter across would be required, while for glass, which is denser than both air and water, a cube 7.4 centimeters across would be required. Each of the cubes of material have the same mass and each receive the same energy, so each would have the same absorbed dose. Looking at this from another viewpoint, consider a combined figure made of these 3 materials in equal volume, say a cube 10 centimeters on each side. Assume that this figure is irradiated and that each region absorbs 1 joule of energy. Because each region has a different mass, each will have a different absorbed dose. The air region will have received 833 Gray, the water region 1 Gray, and the glass 0.4 Grays. The effect of absorbing the energy is also different for the different materials. For example, consider the effect on the temperature of each of our 1 kilogram cubes of air, water and glass receiving an absorbed dose of, say, 1000 Gray. This amount of energy is enough to raise the temperature of the cube of air by 1 degree Celsius. For water, the effect is much less, and a temperature rise of only 1/4 of a degree Celsius will be seen, while for glass, the temperature rise would be larger than for both air and water at 1 1/4 degrees Celsius. When the dose is typical of the limits applied to radiation workers in the public, and the material is biological in nature, it is not the temperature rise that is of concern. Under these circumstances, the concern is that cellular and genetic damage may lead to an increased risk of early death, primarily through an increased likelihood of future cancer development, or an increase in the likelihood of childbirth defects or inherited conditions. These effects are not only dependent upon the energy deposited by the radiation, but also by the type of radiation depositing the energy. For example, alpha radiation is highly ionizing due to its double charge, and because it is relatively easily slowed down, it deposits its energy over a short distance. Because of this, it is 20 times more damaging per Gray of absorbed dose than gamma radiation, as a gamma photon deposits far less energy per unit length of travel. This leads to the concept of an equivalent dose, which is a measure of the biological damage and consequential risk of detrimental effects inflicted by ionizing radiation. To obtain the equivalent dose, the absorbed dose is multiplied by a radiation weighting factor that accounts for its effect on biological tissues. The unit of equivalent dose is the sievert. To obtain an equivalent dose of 1 sievert requires an absorbed dose of 1 Gray of gamma radiation, 1 Gray of beta radiation, or 1/20th of a Gray of alpha radiation, as alpha radiation is 20 times more damaging. The equivalent dose relates to relatively low doses and characterizes the increase in risk of detrimental effects. These are so-called stochastic effects, as they occur at random and with a slightly increased probability over those members of the population who have not been irradiated. The equivalent dose cannot be applied to acute exposure where deterministic effects are seen. Deterministic effects are a direct result of cell damage and occur when a given threshold of radiation exposure is exceeded. Examples are erythema of the skin, induced sterility, and the formation of cataracts. The response to an acute dose typically follows a sigmoid type curve, where the chance of developing symptoms is a function of the dose. Below the threshold, no effects are seen, while at the upper threshold, every patient would develop symptoms.